Good morning, students. So we'll move on to the next topic, that is final state transducers. So we'll see what exactly transducers stand for, right? So inside this, we got a two different topics. First one we call it as a Miller machine, and second one we call it as Moore machine. Okay, so in today's class we'll be discussing about Miller machine first. Okay, so before we move on to the Miller machine, okay, so we'll see what is this finite state transducer means. The finite state machine are used as language recognizers, right? Like whenever we were discussing about a pattern recognition problem, okay, so we need to identify whether the string is in a proper format or not. Okay, for that, what we are using a DFA over there. Okay, so this finite state machine, we are utilizing it for what? Recognizing the pattern of the language, okay, or as language recognition we call it as, okay. That is whether the given language is accepted or rejected by the machine exactly. Okay, if it is in a proper format, okay, then DFA will obviously accept it. Okay, if it is not in the proper format as expected, then it will be rejected. Okay, but we can attach an output for every transition, okay, or for every state. Okay, so previously we were discussing about one particular input string. So we were checking like whether it is accepted or rejected. That's it. Okay, but here in case of the transducer topic, okay, for every state, okay, we are attaching some sort of the output pattern. So okay, so what is the outcome of that particular state? Okay, that also we can attach over there. Fine, but we can attach an output for every transition or for every state. So an input sequence can be converted into sequence of one or more outputs. Okay, so whenever we are moving from start state to the final state towards the final state, okay, along with the input alphabet, okay. Meanwhile, we can generate the outcome of the states over there. Fine, the output of a particular state. Okay, so this process of converting the input data from one form to other form as the output, okay, is called transducers. Okay, so along with the input pattern, okay, whatever we are recognizing from one state to another state, okay, so along with that, using the same input alphabet, using the same state, if we are generating some set of the output, here we are converting the input into output over here. Yeah, so this process we call it as transducers. Okay, so now let us see what is finite state transducers. Okay, so we'll go through what exactly finite state transducers stand for. Okay, so definition we got a finite state machine where an output is associated with either a transition or a state. It's called finite state transducer. It's very simple. Like states will be having two varieties over here. Okay, previously we had only input alphabets, right? Okay, so here we will be having input and also the output. Okay, so if that is possible, okay, then that finite state machine, we are calling it as finite state transducers. When we see the example, then we will be having better knowledge of this. Okay, see, we don't have a separate logic, right? Okay, how we are designing a DFA, same thing we need to do. Okay, so in the question, they used to mention some set of the output representation that we need to set. That's it. Okay, we no need to go for a separate logic and all. Okay, fine. The finite state transducers are associated with output and are classified as shown below. Okay, so first one we call it as a Miller machine, and second one we call it as a Moore machine. Okay, so now first we'll discuss about the Miller machine. Okay, so what is Miller machine, how it will be recognized and all. Okay, and what is the gesture of the Miller machine we'll see. In next video, we will go through the Moore machine. So today we will be solving about Miller machine, total 3 different problems and the procedure for the Miller machine. Okay, so that will be covering for the previous session. Okay, so Miller machine, consider the following Miller machine representation, represented in the form of a transition diagram. Okay, just observe. It is nothing but a DFA which is accepting zeros and ones. Okay, here we are not representing the final state. Okay, we just neglect this E and O, whatever we are having. Okay, see, in every state we are having some input alphabets like 0, 1, 0, 1, right? Okay, see, usually if I make this as a final state, then this is to accept odd number of ones exactly. Okay, if I make this as a final state, then if I make it as a final state, then even number of 1 can be accepted over here. Okay, any number of zeros can be followed by this even number of ones. Okay, so it differs. Okay, if you make this Q0 as a final state, then even number of ones will be accepted. If you make Q1 as a final state, then odd number of 1 will be accepted. Clear? This represents what? Okay, so this is a place which is accepting the even number of 1. This is a place which is accepting the odd number of 1. Okay, so such kind of problem we already solved. Okay, so here Q0, Q1 are the two different state and input alphabets are 0 and 1. Okay, along with that we are representing some E, O here, O, E, okay, something. Okay, so by observing this, if I want to write a transition function for this or transition table for this, then obviously delta function we are using, right? Okay. Okay, fine. So delta function we are using over here. Okay. Q0, Q1. Okay, 0 and 1 we got. Fine. Then over here, we'll be utilizing, as we know, for the transition function, we are using the delta function over here. Okay. But for the output function, okay, if a DFA is attached with the output function, then only we can call it as a millimesh. Okay, that is the only difference. Okay, so here we are using a lambda over here. Okay, so 0 and 1 are the input output, same we need to use. Okay, Q0 and Q1 are the two states, same thing we need to use. Okay, but instead of representing the state, what we need to do, okay, Q1 on receiving 0, observe it, sorry, Q0 on receiving 0, what you have, output function over here, EA. Okay, so for the particular state, on receiving particular alphabet, okay, what is the output we are generating using this particular DFA? That we need to specify in case of the output function. Okay, so delta we are having, lambda we are having, right? Okay, so Q0 on receiving 0, okay, Q0 on receiving 0, it is staying in Q0 itself. If I write Q0, then we are calling it as an input function or as a transition function we are calling it. But instead of that, if we are specifying the outcome of this particular state along with the input alphabet, okay, that we are calling it as output function itself. Q0 on receiving 0, E is the outcome. Then later, Q0 on receiving 1. Q0 on receiving 1. The outcome is O exactly. So O we are writing. Then Q1 on receiving 0. The outcome is what? 0. Sorry, O exactly. See, sorry, don't you confuse? It's O exactly. So O we are writing. Then Q1 on receiving 1. What is the outcome? E exactly. So E we are writing. So this we are considering it as what? Output function, and this we are considering it as a transition function. Okay. If a DFA we are designing along with this kind of output function, then that we are calling it as millimesh. Very simple. Okay. You may ask like how we are writing, why we are writing E and O over here. Okay. So that depends on the question. So when we solve a problem, okay, then you will be having better knowledge about this. Okay. From the above millimesh, okay, observe the following components. The states will be like Q will be equal to Q0, comma Q1. Okay. Then input alphabets. Okay. Each edge is labeled A or O, where A is the input symbol and O is the output. Okay. So here 0 and 1 are the input symbol and denoted by sigma will be equal to 0, comma 1. Okay. So for mentioning the output alphabet, we are using a G. Okay, like half T symbol we are using, but that is not visible because of my taskbar over here. Okay, so the G symbol we are using, okay, half T, which will be equal to, see here, what is the output alphabets we are using over here, or output function values we are using? E and Z, O exactly, right? E and O will be specified over here. Okay, so for the input alphabet, we are using a sigma. For output alphabets, we are using a G symbol, okay, half T. Okay, in the transition function, means what the transition is nothing but change of state after consuming an input symbol. Okay, if there is a change of state from GI to GJ on an input symbol A, then we write it as delta of QI comma A will be equal to QJ exactly. Okay. So as we know, delta we are using it for input like a transition function, and lambda we are using it for output function exactly. Okay. So same thing we need to write. Okay. The output function lambda depends on the current state and the current input symbol. Okay. From current state QI on input symbol A, if the output is O, then we write it as lambda of QI comma A will be equal to O exactly. Okay. Same thing. We don't have any difference. Okay. Here. Delta should be replaced with lambda, okay, and Q0 like state and input alphabet will be same. The outcome, the result, return value of this function will be what? State exactly, but here return value of that will be output. That's it. Okay, we don't have any difference over here. Okay, so these are the what some kind of a definition we can observe it for the melee machine. Okay, then the components as usual how we have for DFA, same thing we are having. Okay, but two things will be added over here. One is what the lambda and one is what the K symbol exactly. Okay, the G symbol, we are using it for what? Representing the alphabets of the output exactly. Sigma, we are using it for input alphabet exactly. Remember, sigma is for input alphabet and G symbol is for output alphabet exactly. And transition function, as usual, delta we are using, but output function we are using a lambda over here. Okay, so the total components over here will be, observe it carefully, the definition. When we go for the definition, the finite state machine where an output is associated with each transition is called Melee machine. Formally, it is defined as M, which is equal to Q comma sigma comma G comma delta comma lambda comma Q naught. Okay, so 1, 2, 3, 4, 5, 6. Total 6 components. Once again, 1, 2, 3, 4, 5, 6 components. Yes. Okay, total 6 different components we got. Okay, so here, one thing you need to observe, like final state is missing. Okay, final state we are not representing in the definition of it. Yeah. Okay. So now, Q is finite set of states. The sigma is the set of input alphabets. Then G is set of output alphabets. Then delta is the transition function. Then lambda is an output function, which is mapped from Q cross sigma to G exactly. Q naught is the start state for the machine. Okay. Then later, now let us see how to construct a Melee machine by taking some specific examples. Okay, so we'll go for the first question. Observe it, construct a Melee machine which accepts strings of zeros and ones. Observe it, strings of zeros and ones. Output even when the input string has even number of ones, and output odd when the input string has odd number of ones. Clear? Okay. So observe it carefully. What we need to design over here? Okay, we need to design something DFA. Okay, which should accept zeros and ones. Okay, strings of zeros and ones. Okay, and it should output what? Even when there is a even number of input string 1, and if it is output, it should output if there is a odd number of 1, then it should output it as odd exactly. Okay, so if we start designing a DFA, obviously like 2 states we need. Okay, so like one state Q0 and another state Q1. Okay, so 2 input strings available over there, 0 and 1 exactly, but the condition is pointing towards what? Even number of ones and odd number of ones. As I mentioned, okay, so this is the place for the even exactly. Okay, so here 0 number of ones if you are having, then you'll be here itself, right? Okay, so even place it is, and it will be an odd place. So Q0 on receiving single one, then it will be going for Q1 exactly. So this will be place of what? Odd exactly, right? See, if you are having 2 ones, 1, 2. Okay, so you are here. When you will be getting even number of 1, you will be in this place. When you are getting odd number of 1, you will be in this place exactly. So let me name it as a odd and even for this. Yeah. Okay. So now observe the following points. In state Q0, the machine accepts strings of zeros and ones having even number of ones. So whenever there is a transition to state Q0, okay, we associate the output E along with input as shown below. Okay. See, whenever we are having a transition towards Q0, okay, there should be having, or any transition which is towards the Q0. Okay, see here 2 transitions are available. One is a self-flip and one is from Q1 to Q0 exactly. So in the both direction, we need to mention E1 exactly. Then what about for Q1 exactly? See, in state Q1, the machine accepts strings of zeros and ones having odd number of ones. So wherever there is transition to state Q1, okay, we associate the output O along with input as shown below. See, these are the 2 varieties. See here, delta Q0 comma 0, delta Q1 comma 1. Okay, so these are the what possibilities of transition towards the Q0 exactly, right? Self-loop we have, one is Q1 to Q0, right? So in the both the values, both the transition, we are having the same return value Q0 itself. So the output function, if I want to write, okay, lambda of Q0 comma 0, then lambda of Q1 comma 1, okay, both are even exactly because it is towards the even state exactly. Okay, but when it comes for the Q1, like odd state it is obviously. So self-loop if you are having, that should be outcome as is O exactly. Okay, and Q0 to Q1, okay, on receiving 1 we have a transition, right? So here also we need to specify it as O exactly. So after doing this, your DFA will be looking like this. Just observe start state. Okay, Q naught. Okay, so it is towards the Q naught itself. So O 0 or E we are writing. Okay, 0 is the input alphabet. E is the outcome. Okay, like that for this also. Okay, here also and here also. Okay. See, in this question, he's not specifying like DFA should accept this particular kind of string and all. Okay, he just mentioned, don't get confused. Melee machine which accepts strings of zeros and one. That's it. Okay, strings of zeros and one. Okay, means alphabet input alphabet will be 0 and 1. Okay, and along with that, one more condition they are specifying. What is that? Okay, Q naught should be specified as even and Q1 should be specified as odd exactly. Okay, then formally the Melee machine to accept even number of ones and odd number of ones can be written as n, which is equal to q comma sigma comma g comma delta comma lambda comma q naught example. Okay, so the next slide, see, just observe. Q will be equal to q naught comma q1. Obviously, sigma will be equal to a comma b. G will be equal to e comma o. Then delta and lambda are shown using the transition table and output function table as shown below. Okay, so these are the outcome. Okay, so now according to this, if you start writing the output, observe it carefully. Q naught on receiving 0, where it is going, Q naught itself. Okay, even. Okay, because see, when you are reaching this particular point, okay, how many number of ones you are having? 0 number of ones. Observe it carefully. How many number of ones you are having? Okay, you may ask like, sir, like one number of 0 we found, but still you are in the position even exactly. See, we are working over what? Even number of 1 or odd number of 1. That's it. Okay. See, can you find any 1 before this point? No, we don't have any 1 available. Okay, 0 number of 1 you are having, right? Okay, but 1 number of 0 you got, forget it. Okay, how many number of zeros, even number, odd number, does not matter exactly, right? Okay, so when you are reaching the Q naught with one single 0, then you will be available with what? 0 number of 1. 0 we are considering it as a even exactly, still you are at even. But later, if you are finding single one, okay, then Q naught to Q1 exactly, right? How many number of ones you found? One number of 1, okay, which is odd exactly. See, what is the outcome we are getting? Odd exactly. Then later, again, if you find 1, then how many number of ones you found? 2 number of ones, which is a even. Then Q naught to, sorry, Q1 to Q naught, okay, which is a place of E exactly, means even exactly. So how many number of ones you found till here? Even. Okay. So later, Q naught on receiving 0, it will be in Q naught itself. Okay. Means even itself. Okay. In Q naught means even itself. So how many number of ones you found? 2, which is even exactly. But later, you are finding one more one. Okay. Then how many number of ones it is? 3, which is odd exactly. Then you will be reaching Q1, okay, which is odd. Yeah. Observe that whenever we have even number of ones, we have the output E exactly. And when we have odd number of ones, we have the output 0 exactly. Fine. So this is how we construct Melee machine. Okay. So next, the second example we'll see. Okay, construct a Melee machine which accepts strings of A's and B's and count the number of times the pattern AB is present in the string. Okay. First, what we are doing here is we are going to design a DFA which identify a pattern AB exactly. Okay. So, like in our regular class, okay, we discussed about the question, designed a DFA which is accepting a string with ending AB, right? Okay, if a string is ending with AB, then it can be accepted. Otherwise, it should be rejected. Okay, for that, we designed a DFA already. I don't want to discuss about that designing again. Okay, so this is what the gesture of a DFA, which is accepting a string ending with AB exactly. See, if it is like AB, AB, BB, AB. Okay, if this is what this thing to be accepted, just observe first what we are having. So you'll be here. B you are having, you'll be here. Then again A you have, you'll be going to Q1, right? Again you have B, you'll be coming for the final state. What you have? Again B you are having. Directly you'll be going for Q0. Okay, then again you have B, double B you are having. So twice you'll be in Q0 itself. Means I'm done with this. I need to go for this now. Okay, so later Q0 to Q1 on receiving A, then Q1 to Q2 on receiving B exactly. So this will be accepted. The question is, okay, DFA like Melee machine should accept the strings of A's and B's. Okay, but what you need to do, you need to count, okay, how many times the AB pattern has occurred. Here, 1, 2, Three times, right? Okay, in this particular string, three times AB pattern has occurred, right? So that we need to count. That's it. Okay, we don't want like whether it is accepting AB or whether it is rejecting the AB. Okay, so change the FSM into Melee machine. Okay, so this is what a finite state machine. Change it to Melee machine. Whenever we encounter the pattern AB, okay, we'll be in final state Q2, right? Here, whenever you find AB, however it may be, okay, after finding triple B, if you are finding AB also, you'll be entering for the final state, okay. So all the transition enters into state Q2, okay, will have the output 1. And for all other transition associated with the output 0. Okay. So here, whenever we are having a transition, okay, everywhere we will be having the output called as 0. Okay. But when you are entering for the final state, if you find AB pattern, then only you will be entering final state, right? Right? If you are having continuous 4 A's here, first day, second day, third day, fourth day, you'll be in final, you'll be non-final state, right? If you are having continuous 3B, like you'll be in Q0 itself. Means when you are entering the Q2, then we have a pattern called as A. Yeah. So when we are having pattern or when we are entering to the Q2, there will be having an outcome called as a 1. Rest of all the transition will be having the output called as a 0. Okay. Later we will count. Okay. How many number of ones we got. Okay. So that is what the total number of AB pattern we will be receiving. Okay. So the Melee machine, how we can design over here is just observe. Okay, the same DFA we are using, Q0, Q1, and Q2. Okay, so Q0, like final state, we don't want exactly for the Melee machine, so we are skipping the final state. Okay, we are making it as a non-final state. Forget it. Okay, here B, self-loop, we have A towards Q1. Okay, self-loop for A. Okay, towards Q0, for Q2, then back to Q1, then back to Q0 exactly. See, everyone is having a output called as 0, right? But only towards Q2, Q1 to Q2 on receiving B will be having a outcome called as what? 1 exactly. Okay, why it is so? See, that is what the entering position for the Q2, right? Entering position for the Q2. Q2 was the final state, right? So this is the state we are entering whenever we find AB exactly. So here we are making it as 1. Okay, if you do so, see, these are the what the transition table and the output function. Forget about it, no problem. Okay, see here, we are using a output or else input pattern called as A, B, B, A, B. How many times AB pattern occurs? Twice exactly, right? Okay, so now we'll see Q0 on receiving A. Q0 on receiving A. What is the output? It will be going for Q1. What is the output? 0 exactly. So whether we found any AB pattern, no. Okay, Q1 on receiving B. Q1 on receiving B. Where it will be going? It will be going to Q2 exactly, right? It will be going for Q2 exactly, right? So Q1 to Q1 on receiving B, it will be going for Q2. But here, see, what is the output of this particular Q1 to Q2? What is the output we found? 1 exactly. Okay, indicates what? 1 times AB occurs. Okay, then Q2 to Q0, what is the outcome? Q2 to Q0, observe the Melee machine skeleton over there. Okay, in the top. Okay, Q2 to Q1, sorry, Q2 to Q0, Q2 to Q0 on receiving B. Okay, so it will be going for Q0. Okay, what is the output? 0 exactly. Because of that, here we are writing 0 exactly. After B, A we are finding, still we are having 0. But when we are finding B, easily we will be going for Q2 exactly. Okay, along with what? 1. That indicates what? How many number of times AB we got? Twice. 1 and 2. Okay, what is the input alphabet? ABB, ABL. So the input string will be ABB, AB exactly. See, once and twice. Yeah. So this is how we are designing Melee machine over there. So here we got one more last example over here. Very simple. Construct a Melee machine which accepts a binary number and produces its equivalent ones complement. Okay, it's equivalent ones complement. Okay, observe it. Binary number it is stating 0 and 1 exactly. 0 and 1 exactly. So any number it may be, but what it should do, it should generate its complement. That's it. Okay. See, we'll begin with Q0 as a 0, 1, 0, then 0, 1. Okay, if you want, you can change also, no issue. Okay, if you want, you can change also, no issue. Here 0, here 1, here 1, here 0. Okay, if you want, you can, no problem. Okay, anything it may be possible. But remember one thing, the output function, whatever we are designing for this, okay, see, if we are having 1, the outcome should be what? 0 exactly. If we are having 0, outcome should be 1 because he is suggesting for what? Okay, it should produce the output of what? It's equivalent complement, one's complement. Okay, what do you mean by complement? If you are having 0, complement of that will be equal to 1 exactly. If you are having 1, complement of that will be equal to what? 0 exactly. Clear? Okay. So now, same thing if you are using, okay. So 1 we are having, so 0 will be its complement. 0 you are having, 1 will be its complement. 0 you have, 1 will be its complement. 1 you are having, 0 will be its complement. Okay. So now we'll consider some input pattern over here. Okay. See, this is what a string we got 10010. Okay. So if in case of this, see, first you are having 1, right? Okay. Q naught on receiving 1. See, 3 things you need to observe: inputs, alphabets. Okay, the Melee machine skeleton and the output function we are writing over here. Q naught on receiving 1. Okay, Q naught on receiving 1. It will be going for Q naught itself. Let it be no issue. What is the output we got? 0. Why? 1 if you are having 0. Okay, it is suggested over here. 1 complement will be 0, right? Then Q naught on receiving 0. Why? Because we are having double 0 next. Q naught on receiving 0. Q naught on receiving 0. It will be going for Q1. Okay. Q naught on receiving 0. It will be going for Q1. Okay. What is the outcome of this particular arc? 1 exactly. So complement of 0 will be 1. Then Q1 on receiving 0. It will be going for Q1 itself. Again, we need to go for a complement of 0. What is that? 1 it is. Then later, Q1. Okay. On receiving 1. Okay, this one, fourth one, Q1 on receiving 1, it will be going for Q0 exactly, right? Okay, Q1 on receiving 1, it will be going for Q0, fine? So because of this, 1 complement will be 0. So here 0 we are getting as an outcome. At last, we are having the last 0. Okay, Q0 on receiving 0, it will be going for Q1 exactly, right? Okay, so 0 we have, here we are having 1 exactly. So complement. Just observe, 10010 we had, right? What is the complement outcome we are having? See, 1 complement of that 0, 0 complement of that 1, 0 complement of that 1, 1 complement of 0, 0 complement of 1. Okay, observe it. We are having a complement of 3 for your reference 0, 1, 1, 0, 1. Okay, so this is what the complement of this particular string, right? 1 complement 0, 0 complement 1, 1, 0, 1 we have. Same thing can we get? Yes. 0, 1, 1, 0, 1. So this is what we call it as Melee machine. Okay. Transducer stand for along with the input operation. Okay. We will be having an output function. That's it. Okay. It's very simple. Don't feel it difficult. Okay. So if you understand or if you listen this video from beginning, okay, then easily you can understand this. Okay. So the same DFA we are designing over here. Okay, don't worry about the final state, whether it is accepted or rejected, does not matter exactly. Okay, but sometimes in case of that particular pattern like AB and all, okay, you can go through, like you'll be practicing few different problems, right, for solving DFA problems and all. Okay, if it is bit similar, design for the DFA, try to check like whether it is acceptable or rejected. Okay, if it is an acceptable state, just remove the final state and just start assigning the output function according to the question. That's it. Fine. So this is it for now, students. So in next class, we'll be discussing about Melee machine. Okay. So that will be the last topic for the module number 1. Okay. Okay, students. Thank you.